Yeah, I think everything is fine. Now, first, if you have any questions, just don't be shy, be brave and ask them. Second, the home assignment is almost ready. I think I will post it today. And the third thing, I'd like to draw your attention to the past exam paper collection, because I think you should look. Okay, so I'm back. I'm back. Please check whether you can hear me. Anyone?
Yes, everything is fine.
Oh, okay. Yeah, so let's continue because there was a minor problem with HSC internet because I'm from, it's not from my home. Okay, so if you have any questions, just don't be shy and ask them. And if there are no questions, let's solve some problems. Any questions? Just say no, yes. If yes, I wait. If no,
no questions. We can proceed.
Okay. So let's consider the following problem. We have covered, I think, the last topic from discrete time case during the last lecture, the optional stopping time theorem. Now let's solve some exercise, the famous abracadabra exercise. It's like it's a famous problem, so you can Google it by name. So it's worth to know it. Oh, it's funny. Okay, so I have a monkey who is typing randomly letters. So each moment of time, monkey will type one letter A, B, C, Z with equal probability. Each letter has the same probability, equal probabilities. And my question is, I observe what the monkey types. And let's imagine tau, the first moment of, so I have enough information so my information ft is just, I know, is generate. So let's imagine some kind, lt is a letter typed, letter at time t. LT is a strange random variable. It's a letter, so it's L1 maybe A, B, Z with probability 1/26, 1/26, and so on. L2, and they're independent. So they're not numeric random variables, but who cares? And my FT, my information, is that I know everything that monkey has typed at time t or before. And tau is the first moment of time when we see abracadabra. It's the first moment of time, minimum t, such that we see, I don't care what is before, maybe it's BBBBB or CCCCC or CD, but we wait for abracadabra. T is here, so it's t minus 1, it's t minus 2, and so on. And the main question is find the expected value of tau, or using the same logic, the same approach, you can find, I don't know, expected value of tau squared. So if you understand the logic, so you can create something more, but I will do only this part of the question. Okay, let's start with the idea. We'd like to create we'd like to use a stopping time theorem, and we'd like that stopping time theorem because it provides a funny way to say that something complex, so let's recall the statement of optional stopping time theorem. Optional stopping time theorem. It says that if MT is a martingale, tau is a stopping time. So there are some technical conditions like A1, A2, A3, but I don't care for the moment. Then, what is the main conclusion of optional stopping time theorem? Who remembers?
That the expected value of m tau is equal to the expected value of m.
Yeah, exactly. You are completely right. The expected value of some complex random variable at this moment of time is just the starting value. In most cases, m0 is a constant. So we initialize the process by some constant. So in most cases, it's even like m0. You even don't need to calculate expected value. So it's a very useful theorem. Something complex at a random moment of time is equal to just the initial constant because roughly like you decide to stop in a fair game. So intuitively, it's very clear because I just stop playing a fair game. If I stop playing a fair game, on average, my final welfare should be equal to initial welfare. If I'm not a prophet and I can predict, it's a good moment to quit because my next profit will be negative. So if I'm not a prophet, if I'm using a honest stopping time, so I cannot, oops, sorry, it's my problem because I just needed to reload. Okay, so let's try, I will show you that sometimes it's possible to create a martingale from nothing. So, okay, let's create a martingale. Let's create a fair game. So let's create some fair game. So we organize a casino. So let's organize a casino. So we have a new casino. We will open a casino with the fair games. If you understand, so let's bet on the next letter. If my bet is right, then let's build some simple rules of a fair game based on monkey typing. So let's imagine that you bet the sum S on the next letter, if you are right, so if you are wrong, you just receive 0. You receive 0. If you are right, then you receive how much? To make it honest, to make it fair game, how much should you receive? That's a small question. How much?
Just 1.
If you bet, okay, if you bet 1 on the next letter, you are wrong, then you receive nothing. If you are right, you should receive, to make it fair. You bet, let's say, next letter, what is a bet? You say something like, next letter will be A. So it's a bet on the next letter. Yeah. Okay. And if you put money, you say $1 or 1 ruble, or next letter will be letter A, and monkey types. And you receive nothing if you are wrong. Oops, if the letter is C, you receive nothing. And if you are right, how much should you receive to make it a fair game, to make it a martingale? So we need to, how much should you receive?
Maybe S?
Maybe 26?
Yeah, 26 or 26S. I have already simplified 1 instead of S. Yes, because the probability that you get the next letter right is small. It's 1 over 26. To make your fortune a martingale, you should receive because this will happen with probability 25 or the 26, yeah? And if you are right, to compensate for low probability of success, to make your welfare a martingale, you should have 26, because there are 26 letters in English alphabet. Then you should receive here 26 with probability 1/26, yeah, okay? And if, so I have one message in the chat, yeah, 26S by Stepan, yeah, Stepan is right. Okay, so these rules should be applied to make a welfare of a player a martingale, okay? If we have such rules of play, then the welfare of each player in our casino is a martingale, okay? Oh, it's too complex.
Because it's a fair game, or what?
Yeah, because so if let's say I have one player, just imagine I have one player. I have one player in my casino, just one player. And what is, let's say, W, yeah, not W, because W we will use for winner process. So let's some RT. RT is a welfare of this player. Welfare of this guy. So let's imagine he enters our casino with $1. What will be the expected value of R1 given F0? He may win $26, but with probability 1/26. He may lose everything he has, but with probability 25/26, and it will give us 1, okay? And by the same way, so R1 is a random variable which takes value 26 or 0, yeah? It's a random variable. So R2, the welfare of my player after 2 stakes is also a random variable, and the best prediction of R2 given F1 will be R1, okay? Yeah?
Yeah, thank you, got it.
If so I organize casino to make welfare of each player a martingale, okay? Yeah, everything is right for the moment?
Yes, yes.
Okay,
Yes.
thank you. Please, please react, because without your reaction, I'm blind. I can't see your eyes, so I don't see whether you are everything is fine. Stepan, thanks very, very much. So just yes, just small no, and it's I need it. Okay, so let's continue. But the problem with this martingale has nothing to do with tau. Yeah, this martingale has nothing to do with tau. So we may apply optional stopping time theorem and say expected value of R tau is expected value of R0 is 1, but it will provide some equations, but this will not be equation on tau. So it's a honest martingale, everything is fine, but this equation has no information about tau. So we'd like to create a martingale of a special form. So we'd like to create a martingale. So we'd like to create martingale MT, something like, do you remember we have created a martingale during the lecture? It was something like ST minus 0.2 point. We have created something like this, yeah? MT equal to ST minus 0T. And in this case, M tau was S tau minus 0.2 tau. And in this case, expected value of M tau has some information about expected value of tau, okay? So during the lecture, we have, in completely another context, we have used a martingale where t appears in a linear, as a linear function inside a martingale. If it is the case, then optional stopping time theorem will give me information about tau, about expected value of tau. Okay, so I'm searching a martingale. So my original martingale RT is a good martingale, but it has no information. So I'm searching something like martingale equals to something minus t. So in this case, when I will apply optional stopping time theorem, I would obtain an equation for expected value of tau. Okay, yeah. And if I have some martingales of the form something minus t squared, then this martingale will allow me to calculate expected value of tau squared. Okay, so if I apply, if I would create a martingale like this, so if I apply optional stopping time theorem, then I would have an equation that expected value of something at tau equals to expected value of tau. Yeah, it will be an equation for expected value of tau. Okay, everything is clear. So what is my goal? I will try to use optional stopping time theorem. Yeah.
Yes, it's clear.
Okay.
So we're looking for a martingale, which would have the information on t, which will become tau eventually, and using this we can find it. Okay.
Yeah, exactly. So because I'm organizing a casino, I'm completely free about the rules. The only idea that I should have a martingale. So I will say each moment I allow entering of one person. So the first person arrives at time moment 1 with $1. That's the rules of my casino. Only one person enters my casino at every moment of time. So at the second moment of time, the second person will enter my casino. So I have a queue. It's a brand new casino. I have a queue of guys who wish to play against monkey, who is typing on keyboard. So there is a queue. Obviously 1.5 meters between them. And they enter one person at one moment of time. And because each brings inside my system $1, the total welfare of all players is not a martingale anymore, because every moment of time, $1 is added inside my system. So I will say that my martingale is a, let's say, total welfare. Well, let's use W. We will use later it for Brownian motion, but for the moment it's okay. So it will be total welfare of all players, total welfare of all players inside casino. Okay, and by construction it is a martingale. We can check that it's a martingale, but by construction we have $1 more on average each moment of time. But we so without this t subtracted, this will not be a martingale. But I add $1 at every moment of time, and I subtract this dollar, like 1 times t. Okay. Everything is fine?
Yes.
So I have created a martingale. So it has the desired form, but for the moment, it has nothing to do with abracadabra. So let's organize, so we are organizing a casino. So we have already a martingale of a desired form, but this martingale should have something with abracadabra. So let's oblige by the rules of our casino that you should bet, for simplicity, to simplify our calculations, let's allow only, you can bet everything on everything. You can bet everything. So you bet on the next letter of the word abracadabra as you enter. So let's, for simplicity, do like this. There are many ways. So it's not only a possible solution, but for simplicity, for simplicity. There are many ways to solve this, but for simplicity, you bet everything you have, everything, on the next letter. So imagine this: t equal to 1, t equal to 2 of the next letter of abracadabra. T equal to 3, t equal to 4, t equal to 5, and so on. The first guy, he enters at the first moment of time. So he bet on A, on B, on R, A, and so on. The second guy, he is not in the casino at t equal to 1. Then he enters the casino and bet on A, B, and so on. The third guy, he is in the queue during t equal to 1 and t equal to 2, and he bet on the letters when he enters, okay? And so on. And let's look at the evolution of the fortune. Imagine that at some moment of time, so imagine that finally the tau arrives. So imagine here we have a happy day, tau day. And we have some abracadabra at tau. The final letter of abracadabra is written. Okay, let's calculate the fortune of every guy. Let's calculate the fortune of every guy. What is the fortune? Fortune of every guy. How many dollars has the first guy?
Could you please one more time explain what's the purpose? So we bet on particular letter, or we bet on the subsequent
Every moment of time, we bet on one letter.
Out of the alphabet, right? Latin alphabet.
Yeah, I have specified.
Yeah,
and the first guy.
Who wins?
Oh, we have specified payoffs. So if you're right.
I mean, if a guy collects abracadabra or what, or if he guesses.
No. We have specified the rules. If you guess right, you have your fortune is multiplied by 26. If you guess wrong, your fortune is 0. It's a martingale.
Because
it's a tough martingale.
I mean, the question is because we're linked to that abracadabra, and they can bet on C on any other letter, not from this word.
Yeah, we have obliged our players. To bet on A, B, R in the following way. So you're obliged to play, but it's a martingale.
Yeah, okay.
They are obliged to play in a fair game. So we have a dictatorship casino. So and you should bet, but the game is fair. Okay, let's calculate the fortune. Because the first, so let's imagine some particular case. Let's imagine that abracadabra is here. Let's imagine that.
Excuse me, can I ask a question about the initial fortune? So when they come to the casino, they all have $1, right?
Yes, every guy. To make it minus T.
So if the first guy comes to the casino, bets on letter A, and he's wrong, then he has
like 0, 0, 0, 0, 0, 0.
So his fortune is 0 starting from time 2 and up to tau, right?
Up to the end of the universe. tau is just the moment when monkey will type, but his fortune is 0 forever.
Okay, thanks.
So if he guess, he has $26. If he guess the second time in a row, he has $26 squared. But if he is wrong on the third guess, he has 0, 0, 0, 0, 0. So the fortune normally evolves like something 1, 26, 26 squared, 0, 0, 0, 0, 0. This is the evolution. Or maybe the fortune may evolve like 1, 0, 0, 0 if you are wrong, starting from the first guess. Or maybe 1, 26, 0, 0, 0, 0. So this is a typical evolution of fortune of our players. But if you are lucky enough, then you will have a lot of money in this game. Okay, so the first guy, is he in the money or not? So,
maybe no, maybe no.
Yeah, that's right. First guy, second guy, third guy. Let's say this is second guy. This is the third guy. And let's imagine this is tau. This is tau. This guy number 4. And monkey C, Z, A, B, Barbara. This is guy number 4. Barbara. Okay, this is tau. Okay, let's calculate the fortune. The first guy, at the moment tau, how much does he have?
0.
0. The second guy is in the money or not in the money?
Not in the money.
Not in the money. The third guy?
26. But wait, no, no money.
No, for simplicity, we have organized so that was the idea of simplicity. At least one error and you have nothing. Okay, the fourth guy is very rich.
26 in the power of the number of letters in abracadabra.
Okay.
No?
So, yeah, exactly. 26 to the power 11. Okay, guy number 5.
It's also 0 then.
Also 0.
And they
Guy
all
number
will
6.
have 0. Also 0.
No, not all. Think a little bit, because abracadabra has, it's a very special word. It has some repetition inside it. So there will be some guys who will be in the money. Who will be in the money?
The last, it's like
4 the last guy. 4. The last guy, the guy number tau, will, because he enters, he bets on A, and he immediately wins $26. And who else will be in the money? There will be one guy more with
the guy who is 4 guys before with Abra.
Yeah, the guy with Abra, because the guy with Abra, he's not present before, but he guessed 4 letters in a row, and he has 26 to the power of 4. Okay. Yeah.
Mm-hmm. Yes.
So we see that our martingale m tau has value. What is the total? So what is the structure? Once again, what was our martingale? Right? Our martingale was something like total welfare of all players at time t minus t. So what will be m tau? It will be what is total welfare of all players at the final moment of time. It's very easy because we have organized such rules to make it easy to calculate total welfare of all players. What is the total welfare of all players at the moment of time when the monkey will type the final letter A of abracadabra?
26 to the power 11 plus 26 plus 26 to the power 4.
Okay, exactly. Minus
Minus
tau.
tau.
Minus tau.
And optional stopping time theorem says, ha, you can calculate expected value of m tau. What is the expected value of m tau? It's m0. It's 0 because before first moment of time you have no one in the casino. The casino is closed. There are no persons, and you subtract 0. And from the other point of view, it should be equal to 26 to the power 11 plus 26 to the power 4 plus 26 minus expected value of tau. Okay? So optional stopping time theorem, I applied there.
Sorry, may I ask a question?
Yes,
About
obviously.
the word. So there is no possibility for someone to have at the moment tau, for example, abracada.
Yes, abracada, he may, but he has no fortune. Yeah, imagine a guy, I don't know his number, abracada, yes, there is a guy, oops, I've mistake. Yes, there is a guy who is in this stage, but if you look carefully, the evolution, oops, and he has, so the evolution of the welfare of this player was 1, 26, 0, 0, 0, 0, 0, 0. So he cannot win.
Okay,
we have very simple rules. Yeah, only 3 guys are in money. Other guys are with 0. They are just, I don't know. They bet 0. Okay? We have solved the problem. So bingo. Yeah. It's a very big number. 26 to the power 11. It's a very big number. So it takes a long time to wait for abracadabra, very long time. So my question is that you can feel that like you are an engineer, you are builders, you can build a martingale, especially to solve a problem. So for example, how would you, my question is, yeah, it's a little bit like art. So it's not like you have a function, you need to calculate the derivative. Yeah, it's a technique. And it's like an art. I'm creating a martingale to use optional stopping time theorem. So my question is, when you have seen such example, my question, how would you modify our martingale to make possible calculate expected value of tau square and variance of tau? How would you modify this martingale? My question, how would you modify a martingale to be able to calculate expected value of tau?
So we should have something minus t squared?
Yeah, you should have something minus t squared, okay. And how would you change the, what would you change in our setup You can change the rules of the casino. You can change initial welfare of players who enters our casino. You can change everything, but what is the easiest way? What would you change? So why we have subtracted t? Why we have not subtracted cosine of t?
We basically should have something like expected value of a martingale at tau t should be equal to m0, right? So we should start from this point, right?
VWT squared. Maybe yes. I haven't checked. My idea was a little bit different. I have not. The idea of Stepan is try something like total welfare squared minus t squared, or maybe some correction. I'm not sure whether this will be a martingale. We need to check it. But my idea was much simpler because our rules are built in such a way that a game inside casino is a martingale. So the easiest way is to change the initial fortune of guys who enters our casino. So that's a good idea. I think it will work. WT minus t squared will not be a martingale, but I think small correction would make it a martingale, and we can go this way. Idea one, I think it's a good idea to square the martingale, correct this process to be a martingale. But my idea is just the same rules inside casino, the same rules inside. It's number 2, but I will change initial welfare of my players because I need that the total welfare on average evolves like a t squared. So if the total welfare on average evolves like t squared, then I will subtract t squared to make it a martingale. So the first guy may enter with 1 ruble, the second guy will enter with how much money? So, okay, why we have subtracted t? Why we have welfare minus t? Why we have casino number 1. First guy is with $1. Second guy is with $1. Third guy enters with $1, and so on. So we have 2, 3, and the total welfare WT expected evolves like t. The total welfare evolved on average like t. So to create a martingale, we subtracted t from total welfare. That was the origin why we have attained expected value of tau. And if we would like to create some other martingale, like WT minus t squared for casino 2, then the average welfare should grow like t squared. So the welfare of the first guy is 1. How much money should bring inside the casino the second player?
4.
If we like. How much?
4.
No. The total welfare should evolve like t squared. Yeah, Evgeny is right. 3. The third guy should bring. So I have 1, 4. The total welfare should evolve like t squared. So the third guy should bring how much?
5.
5. Yeah. So it will be 9 in total. Yeah. Okay. It will be 7, like 16. So if I organize another casino and rules of my casino, if you enter at time t, the security will allow you to enter if you have like 2t minus $1 with you. So the rules of the casino, you enter, at t if you have 2t minus $1. Okay, so that will be the rules of a new casino. I'm a casino magnate. I have a second casino now, and basically, if you continue, you will have expected value of this is WT. Let's say star. Yeah, it will be WT second casino. Will be expected value of tau squared, and you can complete the exercise to solve. Okay, I will not go into further details. You can try to finish the exercise by yourself. Okay, the idea is clear or not?
Yes.
Okay, let's move on to the something, because I think we have finished with discrete time processes, and now let's go into continuous time. Continuous time. So the definition of filtration stays the same. So some definitions are just the same. So once again, before moving to continuous time, any questions with this example? We have calculated expected value of tau. We have not finished the calculations of expected value of tau squared, but the idea is exactly the same. We need to look at another martingale, which has a component t squared inside. And to organize, because I don't like to change anything inside casino, because the rules are very simple and they are martingales and they are linked to abracadabra, so I don't like to lose this link. And so I only changed initial welfare of each player who enters the casino to make a new martingale that contains t squared inside. You just need to calculate possible values of this total welfare squared, sorry, not squared, WT star. What are the possible values of this random variable? And if you understand these values, so you can calculate expected value of this special random variable, and it will be just the value or expected value of tau squared. So just try to finish it. Any questions? If there are questions, I will try to answer them. If there are no questions, I will move to continuous time.
It's clear, seems clear.
Okay, so let's move on to continuous time. Some definitions are just the same. So we have random process is just a sequence of random variable, but now the index t, normally it's from 0 to plus infinity or from minus infinity to plus infinity. So the random process is just an indexed sequence. Random process is just an indexed sequence of random variables. The definition of filtration stays the same. So ft is a filtration if for 2 moments of time, if I have 2 moments of time, S and T, I know more at moment of time T, and for every T, Ft is a sigma algebra for every T. So I have a sequence of sigma algebras that is growing. So the same definition applies to adapted process. Xt is adapted. So definitions are roughly the same. Xt is adapted to Ft if for every T, for all T, Xt is measurable with respect to Ft What else do we have? A martingale. xt is a martingale. So basically all definitions are the same, just to recollect them. xt is a martingale with respect to ft. So it should be adapted plus expected value of some future x given fs is just xs. And we have a stopping time. So all definitions are roughly the same. Stopping time with respect to filtration ft. If tau, I need no brackets because tau is one random variable. I write brackets, that means a sequence. Yeah. So these brackets, round brackets, are they have special meaning. So tau is just one random variable, and xt in brackets is a the whole sequence, a lot of random variables. So ft without brackets is just one sigma algebra. Ft in round brackets is a lot of sigma algebras. Okay, and now something new: Wiener process or Brownian motion. Wiener process or Brownian motion. Brownian motion. A new definition, something new. That's, I think, from the first point of view, it's the most basic process in continuous time, but it's so complex, so interesting. It's a miracle. Okay, we say that Wt is a Wiener process with respect to Ft. Ft is filtration, yeah. If 4 properties or 5, but let's state them and the numbering will. Okay, first property, if. Yeah. First property is very easy. We start at 0. Second property says that increments are independent increments. More formally, if I have some if I'm at moment time s and I look into the future, so I know the evolution of the process up to time s, I'm here. The future is yet unknown to me, and this increment, this Wt minus Ws, is independent. The future change is independent of what I know. Formally, it says that Wt minus Ws is independent of sigma algebra Fs for t greater than s, obviously. Okay, this is the idea that I cannot predict future changes of my process, or the best prediction is just 0. The second property is a normal stationary increments. So I have something like Wt minus Ws has normal distribution with mean 0 and variance t minus s. And finally, fourth property says that probability that trajectory of Wt is continuous is 1. Okay, these are defining properties of Wiener process. Let's just we will not prove that it exists, because from the defining properties it's not clear whether such a process can exist. Yeah, maybe they are contradictory. Yeah, but we will believe that such a process exists, and let's study its further properties. So that will be the way we will go. We will not check the, I don't know, Kolmogorov existence theorem or something else. Just let's pretend there is such process. Okay, let's calculate some properties. Imagine that these 4 properties are satisfied. So first, let's calculate the expected value of WT, the variance of WT, covariance of WT, WS. So first question is like this. B, is WT martingale? C, find HT such that MT equal to WT squared minus HT is a martingale. I think that's enough for the moment. Let's start. Once again, I have these 4 defining properties. These properties define Wiener process. And then let's check further properties. Okay, this is the definition. And let's move on and calculate something more. Okay, what is the expected value of WT? Who can use some properties of Brownian motion and state the properties?
Maybe WS?
No. Let's use the properties. It's expected value of WT minus W0. Why it's so? Because W0 is 0. Yeah. I have used property number 1. Sorry, I cannot show you both list of properties. Oh, maybe you can just look at, I don't know, some Wikipedia article, Wiener process. I think there are these Wiener process. I understand that it's easy to look, because if I would have a whiteboard, but okay, so just what can I do? I can make a photo and send in the chat. So let's do like this. I will copy Jbunk, and I can send it here. Okay, so it's by first property, but by property number 3, this difference is normally distributed with mean 0 and variance t minus 0, so it's 0 by property 3. Okay, what is the variance of WT? Be brave, it's easy. Just look at the properties. It's not a WT, not 1. Once again, it's variance of WT minus W0, because W0 is 0. And according to the definition, what is the distribution of difference?
Normal with expected value 0 and variance t minus 0. Oh, sorry.
Yes. And variance t minus 0. Okay. Okay, we have calculated.
Yes.
Okay, let's calculate covariance. I imagine that S is less than T. If it's greater than T, just change lettering. So I don't care. So let's imagine S is less than T, but it's not important. So you may say S greater than T, and the answer will be inversed. WTS. Because we have independence property. Yeah, we have independence property. So it's great to think in terms of future increments. So I would say that it's covariance of WS plus WT minus WS with WS, because I know that this term is independent of Fs, and Fs is I know because my process is adapted, and oh, I missed it. I missed the I missed it. Yeah, WT is adapted. Sorry, I have missed. Is adapted to FT, but it's a standard assumption. We need something that we can calculate the value if we have our information, but it should be pointed. Okay, so Fs is just information generated by all WU for U lower than S. So this increment is, so first covariance of WS with WS plus covariance of future increment with WS. The first term is just S because we know that it's a variance. Yeah, we have already calculated variance. And the second term is equal to once again, I know that W future increment is independent of all information of WS, of WS minus 0.7, of WS minus 0.5, of WS minus, of all previous WS. So what this assumption says, once again, this increment, the future increment, is independent of all what I know up to time S. Okay, so any combinations of what I know these random variables are independent from future increment. So that means that this increment is independent of, I don't know, WS, W0, WS over 2 of any, or I don't know. So this increment is independent of all what I know at moment S. And then in moment S, I know Fs and many values before it. Okay. So my main point of my main remark is that they are independent. These two random variables are independent because these random variable WS is known at S, and everything that is known at time S, past information, gives me no information about future increment, and this is future increment. This is future increment. And this is my information at time s, okay? These are random variables, they're independent, and the covariance is, Stepan says that is 0. And the final answer is S. Okay? Any questions?
Clear.
Okay, let's check whether WT is a martingale. So we need to calculate expected value B so it's adapted. So we need to check WT given Fs. S is less than T. I use the same idea. I represent my future value. That's an easy trick. Future value is like past value plus change. That's very, I don't know, it's more or less obvious. Yeah, I don't like the word obvious, but I think in this situation we can say it. Ws plus Vt minus Vs given Fs. And once again, we are working with conditional expected value. This random variable is known at time s, and this difference is independent of what we know at time s. So by the properties of conditional expected value, what do we have?
Expected value of Ws.
You know it. You are almost right, but not completely. If I know
Ws plus
yeah,
value of Vt minus Vs.
Yeah, I know that so let's do it step by step. By linearity, it's expected value of Ws given Fs plus expected value of Wt minus Ws given Fs. So this is completely known to me. My best prediction of Ws, if I know it, it's Ws. My information in the second case is completely useless to predict. So I use ordinary unconditional expected value. And it's 0. We already have used it. So is it a martingale or not?
Yes, it is.
Yes, it's a martingale. Okay. Yeah, that's great, I think. Yeah. Let's check whether we need. So let's check Wt squared given Fs. I will leave you the choice of the function. Just let's calculate expected value of Wt squared plus Fs. I use the same easy trick. Future is past plus change. So it's Ws squared plus, Ws plus Wt minus Ws squared given Fs. So I use the same trick. I decompose future value into two blocks. Block what I know and block which is completely independent of what I know. So it will be expected value of Ws squared plus Vt minus Vs squared plus 2 Vt minus Vs given Fs. So now I have 3 terms in my expected value. The first one, what is the best guess of Vs squared if we know everything at time s and before? What is the value of expected value of Vt minus Vs squared given Fs? And what is the value of Ws Vt minus Vs given Fs? How can I simplify the first term?
VS squared.
With variance, maybe.
No. I know it completely.
Then it's V
It's
squared.
completely predictable. It's known. So it's just WS squared. Okay, here this part is independent. So I just omit what I know. My information is useless to predict future increments. Future increments are independent of what I know. So just ordinary expected value. In the last case, I know WS. So for me, WS is a completely predictable function. So I just move it out of the expected value. And I have 2WS. Oops, let's go back to black. 2WS expected value of WT minus WS given FS. Because you can move out of the expected value what is known. And finally, it's WS squared. What is the value of this expected value?
Zero?
Wow, something that is positive. It's very strange. When you meet something who says that expected value of something positive is 0, you should be very careful. Maybe.
But VT minus VS is distributed normally with 0 mean, right?
Yeah, but it's squared.
Mm-hmm. Okay.
So without square, you're completely right. So it's variance of WT minus WS plus expected value squared of WT minus WS. How to calculate the expected value of hedgehog squared? It's variance of hedgehog plus expected value squared of hedgehog. Yeah. Plus. And here once again, I can omit all information I have because it's useless to predict future increment, and expected value of future increment is 0, so it will be 0. And finally, I have WS squared plus T minus S. This is expected value of WT squared given Fs. And you should guess the function, so we see that it is not a martingale. So WT squared by itself is not a martingale. And the question about the correct correction term is left to you. Any questions?
So how did we get the last expression, which is WS squared plus T minus S? It's just after the simplification of the equation above, right? Of the expression above.
It's here is WS squared.
Yes.
Whereas
here is 0. Yeah, it's just a simplification of expression above. Yeah. Okay. Got it. Thank you.
Yeah. And this term is this is also 0. By properties of Brownian motion, these are assumption numbers V, as I remember, or maybe 2. We have stated that it has normal distribution. Okay, if there are no questions, then thank you.
May I ask a question?
Yes.
Maybe I missed something by why the covariance of WS and WS is S? Or maybe I've forgotten something.
Random variable with itself is variance. So if you calculate, so variance of WT is T, but it's covariance of WT with WT. We have proven this before and we use it.
Yeah, okay. Got it, thank
you. With T replaced by S, of course.
Yeah, sure. Thanks.
Sorry, can you please explain once again what is independent of what? With respect to those future value, past value?
Future increment. So this is now. This is future increment. Future. So this is T. This is S. So information we know is Fs. Info we have Fs. And there are many random variables that we can state the values. So let's imagine S is 5 and T is 10, okay? So you know information F5, which random variables are measurable with respect to F5? Which values can you calculate? Let me write a small list. Measurable with respect to F5. For example, you know the value of W5. You know the value of W4. You know the value of W3.5. You know the value of cosine W4.5. You know 4.5 divided by 4.3. All these variables are known to you. So your information is sufficient to calculate the value of these random variables, okay? First question, you need to understand which variables are measurable with respect to your information. If you understand this point, then the answer is simple. Future increment is independent of everything you know. So W10 minus W5 future increment is independent of this big list. This list is, I have written just some members of this list. Okay?
Yes, okay, thanks.
So you should understand, what do you know, which random variables are measurable with respect to your sigma algebra. This is a big list. There are infinitely many random variables, and all of them, they are dependent among themselves. Obviously, these random variables are dependent, yeah? W5 and this ratio obviously are dependent. They are dependent among them, but any member of this list is independent with future increment. Your information has nothing to do with future change. So you cannot predict whether the Brownian motion will go up or will go down.
Okay, thanks a lot.
By calculating logarithms, cosines, or anything of your information. Okay, then thank you for the class. Have a nice day.
Thank you too. You too.
Thank you. Bye.
Bye bye.